My name is Julien. I live on the other side of the street, that side, MIT. I'm really glad to be here today, thanks to SOFA, the couch collaboration initiated by Nico, a roommate. So in the talk, you'll see how we can merge everything, owing to the fact that data science relates on very transferable skills. So everything we do can be moved from one field to the next, leading to mutually beneficial collaborations. And that's really the point of this talk. The beauty of planetary science, where I play, and biology, where Nico's play, is that these fields are highly multidisciplinary, meaning that we need to rely on a lot of expertise to gather data consistently and extract as much as we can out of them. So, in both fields, we have to extract build theories. So how do we do this? To extract a theory, let's say, to find out how, that is not coming up well, that's okay, fine. So to extract how happy, satisfied people are with life, for example, as a function of different metrics, you go to some individuals, some families, and you sample them. So you gather data points as a function in a given parameter space. And you try to make sure that each of these data points are reliable. You extract accurate measurements that are relevant to the question you ask. And then you make sure that you're investigating enough dimension in your parameter space. Where are the people from? How much diversity is there in each of the country? What trend you can extract in this cluster of points? What age distribution relates to each of these samples? So to really build a theory, what you need is a perspective that is accurate at the sample level. Make sure that you have really reliable measurements, so you know what's going on, what is the black box that allows you to plot this point right there. Thorough, in the sense that you're investigating all the relevant dimension in your parameter space. And broad, allowing you to sample adequately to populate your posterior probability distribution. You're gathering enough sample. So this is only feasible when you start to develop standardized procedures. Now, if you look at fields such as biology, planetary science, it always moves over two different timestamps. There is a first timestamp of exploration, innovation. You move through the new dimensions, you develop innovative techniques for limited samples, 1, 2, that's it. And then you need to crystallize these different techniques to allow you to spread them across the parameter space to extract the big pictures. So I'll give you an example of how it works in my field, planetary science, in the context of exoplanetary science, the study of planets around other stars. So as you know, for centuries, our understanding of planetary system, planet formation, planet evolution has been based on one sample of the solar system. That's it. We've been able to dig about 12 kilometers deep in our Earth, which is 6,000 kilometers deep, technically. We've been able to probe the first 100 kilometers of our sun's atmosphere, independently of the wavelengths we looked at through. Yet, thanks to this, we've put together a pretty consistent story about our system. Consistent for one sample. About 20 years ago, we started to discover exoplanets. The first one, 51 PEG. We also have complicated name in planetary science. Don't be proud of your own. We've discovered 51 PEG. It's plotted here on a graph that shows mass of the planet as a function of the orbital period. For reference, you have the one in the solar system, Mercury, Mars, Venus, the Earth, Uranus, Neptune, and so on. And then, over the last 2 decades, we managed to already discover over 3,500 planets in over 2,500 planetary systems, meaning that our sample size has increased by 3 orders of magnitude. Owing to this, we've placed the first observational constraint on the planetary population in our galaxy. We know that there is at least 1 planet per star in our galaxy, meaning that there are at least 200 to 300 millions of planets orbiting their star. But that's not it. Next to providing this observational constraint, we've challenged our own perspective, our own story standing on one single data point. We find new planet types. Planet like hot Jupiters of the size, yep?
The data, you might be going to talk about this, but the data that you're presenting looks like our system is different from anything else that you've measured.
Yeah, these are observational biased. So I can come to that. It's easier to detect planets that are closer to the star in terms of just likelihood so the strength of the signal and also likelihood of detecting them based on the frequency of the signal to be detected. So these are observational bias. We're moving there. So if I go back, you'll see that we're detecting planet here, and as years pass by, we're moving down here.
So most planets we haven't come close to seeing, even in these systems.
No, I mean we have 3,000.
No, I don't mean that. I mean given that
here?
bias that's referred to.
No, we're not tackling
We
this.
see about 1/10 of the planets, even in the places you're looking.
Correct. So it's really is a work in progress, which is the whole point of the talk. In these 2 dimensions, there are new space to be explored, and we're getting there. So new planet types, planet with no analog in our system, like hot Jupiters, planet of the size of Jupiter, but that orbits a star not in 11 years, but in only a couple of days, meaning that the average temperature is thousands of Kelvin. Super Earths, planet with sizes that range between the largest rocky planet in our system and the smallest ice giant, meaning that there are lots of them, but we don't even know their nature a priori. Are they a large rocky planet or small ball of gas? And next to that, we found planet without star, free-floating as a galaxy. We found planet with multiple stars, like Kepler 16b, that offers iconic double sunset like Tatooine in Star Wars. We find planet.
How do you find the free-floating planets? You find planets by watching them block the star.
No, there are lots of. Okay, so I was about to talk about main techniques, but the way this works is we use, for example, either gravitational lensing. So you look at a field, and when something relatively massive passes in front or close to a star, then you have a spike due to the gravitational lensing of the star and or a planet. So this is luck for these kind of stars. So we find planets extremely exotic, like this one, J1407b, that has 37 rings, 200 times the extent of Saturn's. So big that if Saturn had such rings, you'll be able to see it by naked eye in the sky, and it will be larger than our moon. We find planets currently be dying around their stars, being pulled apart by the gravitational field. That's how much we've learned, that's how much our perspective has been changed already just by detection in the context of planetary science. So the way we detect this planet, as you just said, is twofold. These are the main techniques. There are other techniques. First thing is to look for the light, the brightness dip of the star when something passes in front of it. Now keep in mind that these systems are so far away that you don't resolve it. You don't see the star, you don't see the planet. Everything, the whole light coming from the planetary system is condensed in one bright spot. So you can study how the brightness of this spot changes with the wavelength or with time. When you look with time, you can search for this brightness dip, which relates directly to the area ratio of the star to the planet, so it provides you with a constraint on the radius of the planet. And then if you look for wavelength change, you go to the radial velocity technique, which search for the Doppler effect induced by the gravitational pull of the planet on the star, on the emission spectrum of the star. And because this pull, it's basically like an ambulance. Think about the emission of an ambulance, the sound of an ambulance coming towards you, you reach higher pitch. Going away from you, you reach lower pitch. And this gets constrained on the mass of the planet. Yep?
Do you see that sort of dimming without seeing the Doppler shift? Are there phenomena that look like the data on the left that are some other function of the star?
So to answer the first part of your question, some planets are only detectable with the transit because they are so faint that you cannot detect. They are so small or not massive enough to actually touch the star for us to detect the signal. And then, there are other effects that looks like these oscillations, which relate to the activity of the star itself. So they are systematic so the star oscillates, rotates, it's not just a flat surface. So at the surface of the star itself, you have masses that moves towards you and they're away from you as there's buoyancy at the surface of the star. So there are lots of additional signals that may look like planets, but then you do periodograms, so you do frequency analysis to try to extract different signals in their structures. So thinking about dimension space, we are able for some of the planets to plot them in a radius mass diagram, period or so, and then you can start to talk about their bulk density, disentangled from giant ball of gas to rocky planet to giant ball of iron. But that's not it, right? If you really want to extract the big picture, start to talk about climates on other planets in the grand scheme of things, talk about distribution of habitats, life in the galaxy, what you want to do is dive deeper, dive in the atmosphere of the planet. Yes.
Sorry, could you explain a little bit about mass? If you don't know the mass of the star, how do you figure out the mass of the...
So you have...
I mean, you know the Doppler shift, I get that,
yeah.
which probably gives you a mass ratio. Mm-hmm. But that's not mass.
No, you have the mass of the star from an evolution regime, so based on the stellar type, you know, and its age, you can constrain its mass, temperature, and all the things.
I see. So you know the ballpark of the mass of the star by the emission spectrum itself.
Yep.
And
parallax
then
information.
you have the ratio from the Doppler shift, and that's how you get the ballpark.
Yes. Yeah. Well, technically, you don't even have the mass. You have the projected mass. It's m sine I, because you only have the radial velocity in your direction.
Sure.
You don't know there. But if it's transiting, then you have the inclination, and you can extract the mass. Good. So, diving into the atmosphere of planets, we use currently facilities that were designed. This is a key point. We use facilities that were designed even before we started to detect exoplanet, and yet we can do extremely cool science. So I'll go into the future in a bit. So what we do, we use transmission spectroscopy, and we look at how the light coming from the star passing through the planet atmosphere is affected by it, meaning that at some wavelength, you would have absorption, at other not so much. So if we have a planet in front of a star, and its atmosphere is opaque at a wavelength lambda 1, but not at lambda 2, you would have an additional contribution for the flux drop due to this opaque atmospheric annulus here. And so the transit depth at lambda 1 will be deeper than it is at lambda 1. So there's a wavelength-dependent transit depth when the planet passes in front of the star. So quick application, if you look for the hot Jupiter HD 219458b, here observed with Hubble in 2013, so you have the transit depth as a function of the wavelengths between 1.1 and 1.7 micron. You see an increase here by about 1.5%. What could it be? So, as I said, this is the light interacting with something in the atmosphere of the planet. So we write into spectroscopy. So you turn to your favorite quantum mechanician and ask what could be happening in the planet atmosphere at these wavelengths. You compute the absorption list, you extract the molecular features, and you can show that there is water in the atmosphere of this hot Jupiter. So this is a very basic, what we've been able to do already. Now, sorry, water, yeah, there you go. Now, this is what awaits. Facilities that looks way cooler than what we have currently, let's face it, but also with completely different capabilities. Way larger collecting aperture, which means exquisite data quality, higher signal-to-noise ratio. You collect more photon, Poisson noise, you reduce your error bar by square root of n. High spectral resolution, meaning that this feature that I was talking about here, we can actually sample it and extract more than just, oh, there's water there. We can say how much water, at what pressure and temperature as well. And then finally, extended spectral coverage, which means that this is the kind of data that we would have for mid-Neptune, meaning a Neptune-type planet, but of the size of 3 or 4 times the Earth. And you can compare to what I just showed you before. This was the range that was covered by the Hubble Space Telescope. So way more molecular feature to extract, so you can really start to probe the temperature, pressure, and composition profile of other planet atmosphere. So we're really moving, at the end of the day, to an era of high-throughput planetology. High throughput in the sense that lots of planets within hands, but also amazing data sets and very dense insights into their properties. To give you another example before diving into this exciting topic of TRAPPIST-1 and the search for extraterrestrial habitats, let's talk about how we can actually map exoplanets. So if you remember, if you think about planets, this is what you typically have in mind, things that you can spatially resolve. You can differentiate different points, see patterns, rings, but exoplanet has nothing to do with that. I'm going to zoom in as much as we can into one of the Rosetta Stone, one of the systems that's the best, the most studied so far, HD 189733. It has a hot Jupiter that's great for different types of study. So we zoom, and that's as far as we can go. Everything, as I said before, is condensed on one point, spread on a couple of pixels, so we're really just doing time series, right? So how can we map exoplanet while all we have is that?
Does that include the sun? The star at that point?
Oh yeah, that's everything. That's the star, the planet, everything is in there. Oh yeah?
12 pixels.
Yeah. So how can we actually map a planet when we cannot even resolve the star, right? Star which is like a million times brighter, bigger, everything. Well, as I said, we have a flux. That change is a function of time and wavelength, and wavelengths. And it's by leveraging this variability and understanding what can hide behind it that we can do the job. The first thing that we can do is look how the flux change as a function of time due to the fact that, yes, there are variability from the star, but also that the planet rotates upon itself. And from that, you can extract phase curve that you can convert into longitudinal map. Because as the planet rotates, the angle of each of these different slices changes, and some are disappearing while others are reappearing. So you can start to map the brightness distribution, which relates to temperature or composition distribution over the globe of the planet. But we can go further. We don't have to be limited to 1D. 2012, I started working on eclipse mapping. And the idea of it is when a planet passes behind its star, it is scanned in one direction during the ingress, and then it reappears in the other with the scanning process in the other direction during the egress. So if you monitor carefully the flux variation during this process, what you can do is you can search for deviation in the signal of the flux drop when the planet is being hidden by the star, due to the fact that the brightness distribution is not uniform, but actually for some of the planets we have like very massive hotspots. I'm going to explain why. For hot Jupiters, these planets are so close to their star that they are tidally locked. Like the moon always shows the same phase to the Earth, this planet always shows the same phase to their star, meaning that there is a permanent day side and a permanent night side. And so it's really important for us to study how this energy is deposited in the atmosphere of the planet and then blown away, redistributed by very strong winds that goes from the day side to the night side. So we know that there are hotspots on these planets, studying what is their magnitude, how they are dissipated in longitude, latitude, and pushed towards the night side help us understand the climate of these planets. So it's pretty cool to be able to move towards this 2D mapping. So the idea really is to look at how the flux drop relates to brightness of a slice in different directions, and then you can recombine and create a map. Ideally, you don't recombine, you do everything at the same time in the context of global analysis, but I'll skip this for now. So, I'm going to talk about caveats now quickly. Sorry.
Is this how you tell whether the planet is rotating, or do you have another method for that?
To
know whether the planet is rotating or whether it's staying facing the sun.
So this application here is known for tidally locked planets so far. So we know that they always show the same face to the star. You can do this once you move to facilities that allow you to do one map per eclipse. So far what we need to do is combine different eclipses and then to push down the signal to noise ratio, to push up the signal to noise ratio. Then you can move to non-tidally locked planet and just do maps. Yeah. Now, something I always speak to you relates to caveats. So now this was about planetary science. I'm going to keep on diving into this, but I'm going to synthesize the takeaway message for this section in a sec. The takeaway message is that you have to pay attention to multiple contributing factors. In this case, the signal that we need to do the map is correlated with other things. Other things contribute to the shape of the ingress and egress. For example, the shape of the planet. Impact parameter, which tells you, depending on the orbital configuration, where the planet passes behind its star. So what is the angle of the stellar limb that will be scanning the planet, and this affects the shape of the ingress-egress, obviously. The size of the star, and then the eccentricity, which in two different ways describe what will be the speed of the planet at these different points, and so also the shape and the asymmetry of these signals. So we are playing in a highly correlated parameter space between the map, which is what we want, the shape of the planet, and its orbital configuration. And so what needs to be done in these things, which is, yeah.
Sorry, I have
Go.
lots of questions. It looks like to do this, you would need to observe multiple transitions of the same planet.
Yeah, correct.
But if I'm trying to think about a star like Jupiter, where the orbit is a bit long, how are you going to actually end up doing that?
So for this,
is this related to what you said about the bias, that you You can only find planets that transit very...
So this was done for, so the first time we did this was for a planet that has a period of about 2 days. So every 2 days it's happening. Now, there is a correlation, direct correlation between the period, orbital period, and the duration of the event.
Sure.
If Jupiter were to transit, it will take so long that you don't need to gather much data. You're gathering it right away, as it's like, you know, the number of photons relates directly to the time it takes to passes behind it. So you would collect way more, well, enough photon to do this with future facilities. Because Jupiter is so far from its star that its temperature is cooler. This planet has the one for which we work is temperature of 1200 Kelvin or so. So it all relates to observation time plus occurrence rates, which will be pretty low. Keep in mind that we need the planet to pass behind its star. Jupiter is so far away from the sun that the likelihood of having something passing under it is pretty low. However, something that I've been considering is synthetically doing the scanning. The idea is you use interferometry to have fringes in your field of view where you have positive and negative constructive and destructive interaction of light. So you can actually scan the planet yourself by shifting these different fringes. So it's another way of doing it. But the idea remains the same. Does that answer your question?
Kind of. Thank you.
You're welcome. So we are in a highly correlated parameter space. And to do a good job in highly correlated parameter space and correlated space as a whole, there's something fundamental that needs to be done, is to relax unverified assumption. Way too frequently people are overlooking this, and it's really important for two reasons. If you have a highly correlated, a correlated parameter space, your posterior probability distribution, your confidence interval, will be quite complex in your parameter space. And if you keep assumptions, what you're doing, you're basically slicing it, which is going to lead to two things. First, you're going to underestimate your error bar or overestimate your precision. And then second, if one of these unverified assumptions appears to be wrong, for example here, you assume the eccentricity or the obliquity of the orbit to be 0 while it's not, there's a slightly residue. You're going to bias the estimate of all the parameters that are related to it in the context of this correlation. So you have to release this assumption and then move to a larger parameter space by bringing complementary data and perform a global analysis by fitting everything together to help constrain this whole massive correlated distribution. Good. So I won't dive into the detail of how we do, but basically if you add some transit data, then you can help constrain the shape of the planet, and other things help you, boom, fit everything together at the same time, get a 2D map. Is that it? No. To help you, well, the thing is, I don't want to spend too much time on what this means and where that goes. Just want to give you a vibe of how much we'll be able to do in this context of moving to high throughput and the depths of the insight that are within reach for other worlds. So
let me ask you though, if people were interested to read more, what would be the best place to look for these details? Is it the Nature paper appendix, something else?
No, this is another work back in 2012. So I'm gonna...
Just send me some things and I'll make sure they're available on
Sure.
the website.
Okay. Good. So we can do 2D maps of planets, but we can do better. If you remember, I was looking at the time variation, but also looking at the wavelength variation. Opacity of the atmosphere is dependent on the wavelengths. At some wavelengths, you will probe deep because the atmosphere is mainly transparent. At other wavelengths, you will not. And so if you do this kind of observation at different wavelengths, you can move to 3D map of exoplanets. Different wavelengths probe different altitude depths, and each of these observations can bring you constraint on the latitudinal and longitudinal brightness distribution. So you can look at how the energy is deposited and then shifted at different depths. And this is something we've been able to do with a facility, again, designed in the 90s. So what we're going to have in the future is the capability with something like the James Webb Space Telescope to have a very precise 3D map of exoplanet atmosphere in latitude, longitude, and altitude, allowing us to study the 3D pattern or the weather of the 3D pattern in the atmosphere of other worlds. So really dive super deep. So now we have an idea of how far we'll be able to go, and this goes in the context of high throughput in terms of wealth of information and in terms of number of planets we'll be able to get this data on. Great. Now let's go back to the cool stuff, the search for extrasolar habitats. Not that the rest was not cool, but so a couple of months ago now, we announced in DC the discovery of 7 Earth-sized planets. And why is that so cool? Well, these planets are the first ones that have this winning combination of being Earth-sized, temperate, so potentially habitable, and they are amenable for in-depth study. And that is a cool part. We can actually do something cool with them. If you want to know more about this, you can go on TRAPPIST.one, and we gather all the information over there.
It's so cool. They're different colors, different textures.
Yeah, see what you can do with a mapping
Just
technique.
incredible.
Well, don't look at that. So, yeah, but that being said, there are, like, we worked with actual climate, so we have climate people in our team, so we try to have something that's somehow consistent, but of course, it's...
Artist conception.
Yes. Which somehow helps with the public. I don't know why. And funding. I don't know why. Anyway, so, these planets were detected initially with a robotic and a prototype telescope. It's only like a 60-centimeter telescope back in Chile, Belgian telescope, hence the acronym, far-fetched, but yeah, still pretty cool. And this telescope, thanks to this telescope, we reported in May 2016 the discovery of the 3 first planets, and then we pushed, we initiated a worldwide effort that already provided us with 4 more planets, and we're still counting. What is really cool with this system relates to the size of its star. If you remember, when I talk about transits, what really mattered was the planet-to-star area ratio. This is the same thing in transmission. The smaller the star, the larger the relative signal of the planet. Here you have a star that is about 10 times smaller than our sun, meaning that the signal of planet, Earth-sized planet, or any planet, in front of it is about 100 times larger than what it would be in front of our sun. And that is why it's essential. This is why Michael Gillon, the PI of TRAPPIST, pushed to search for planets around this star. And so far, he had only looked at about 40 stars like TRAPPIST-1, and he already led to this detection with this prototype. So, and we actually extended the network. I was last week in Chile, and we're putting like 4 new telescopes of 1 meter down there, and we're raising funding here at MIT to do the same thing in the northern sky. Good. So, in terms of size, TRAPPIST-1 is actually about the size of Jupiter. Now, the fact that these planets are amenable for in-depth study means that they are providing us with the first opportunity we have to search for signs of habitability in cells of life, but also the first opportunity to really revisit our understanding of planetary system. The nice and smooth story we build based on this one sample can be challenged thanks to the depths of the insight we'll get from this system. Now, to push a bit further this perspective, this star, TRAPPIST-1, is an ultra-cool dwarf star. This is the type of star that is the most frequent in our galaxy. And it has been able to form not 1, not 2, but 7 terrestrial planets, way more than our star. Meaning that what you're looking at here, these red worlds, may well be the archetypical terrestrial planets in our galaxy, something that we would just not have thought of. Meaning that if life were to develop there, or if they are like habitats, there will be the archetypical habitats that are populating our galaxy. And another interesting element is that these stars live forever. Good. Now, with the effort we've initiated ranged from the extraviolet down to radio. In extraviolet UV, we search for atmospheric escape. In radio, we search for magnetic field. And we're also working with the SETI people to search for other type of signal, the kind of signal that Jodie Foster was looking for in contact. But what I do is, next to the support, next to searching for the planet, my role is also taking the lead for the atmospheric characterization. So, how do we study the atmosphere of such world, really probe them? Go back to transmission spectroscopy. What we do, we look at how the transit depth changed as a function of the wavelengths. So, the idea of MIA is to push you a bit through data science, so I'm going to dive a bit deeper with a practice here. So the idea is I'm going to talk to you about a data set and walk through the process of data acquisition, data crunching, providing you with a link to the data online because the data are not publicly available. So you can, if you want, just write your pipeline in a couple of weeks and get what we got here. So on May the 4th, just 2 days after we reported the discovery, we realized that there would be a really good event happening for us. Two of the planets, the two innermost planets, will be passing in front of the star, meaning that we could grasp the first insight into the atmosphere of Earth-sized planets at the same time for two. So that's a pretty cool day, which we did. This is Hubble data I gathered. We have the flux before. These are windows where Hubble cannot observe because Hubble is on a Earth orbit, meaning that from time to time the Earth is blocking the system. And yet everything was wonderfully aligned. The Earth, the two planets, and Hubble to provide us with this double transit, TRAPPIST-1c and then TRAPPIST-1b next to it, allowing us to get at the same time insight into the atmosphere of the two planets. You have the data in black that are relatively flat compared to what we were expected not to see, so it's a good thing. So transit depth is a function of the wavelengths. This quick pre-screening aimed at one thing: look for the presence of hydrogen-dominated atmosphere. If that's the case, these atmospheres are really big, puffy, and large. So the atmospheric annulus is thick. So the amplitude of the transit depth variation as a function of the wavelengths are pretty wide, and we didn't detect that, which is a good thing because hydrogen-dominated atmosphere would have mean not habitable. Hydrogen is a very powerful greenhouse gas. So how did we get to that point with one observation in practice? So we knew this was happening. Data acquisition is the first step. We reached out to NASA, got Hubble, a quick proposal on Hubble accepted, pointed at the star. So you have the detector here. This is an image of the star, well, of the whole system, obviously, right there. What we're looking at is wavelengths-dependent information. So you put a prism on it, a grism, and then you split the light as a function of the wavelengths between about 1 micron to 1.7 to help with the integration and the overhead time, duty cycle. What you do is you allow the telescope to drift a bit, so you spread the light over time, and you don't have to make too many acquisitions, so you increase your duty cycle. Great. So, step one, using robust facilities, standard procedure. So the idea is data acquisition with standardized procedure. When Nico will move to his stuff, I know he's not going to talk about the amount of time he spent on his protocol to reach the data set that he has, but that is really important. Data acquisition made with robust procedures. Great. Step two, data reduction. So if you want to get the data, you can go on this website, you enter TRAPPIST-1 as a target name, press enter, and then you can mark the file that relates to this proposal, and then you can get these frames. So you end up with spectrum at different times, but you can see that it is quite crappy. There's a lot of stuff on this. You have cosmic. Cosmics relate to high energy particles that are just traveling space and decide to crunch on your detector. And then you have the spectrum that's slightly tilted, shifted, and not exactly at the right position. So you do some data cleaning, subtract the background, traditional things. That in most cases for you is done automatically by the machine. That's why they're so expensive. And then once you end up on this, pretty simple. You build some tiny cases and you integrate the flux in different bands, so you can end up ideally with something that like this. In different channel, you science data. So the baseline when nothing is happening, transit of C, transit of B, nothing is happening as a function of the wavelengths. Is that it? Nope. Why? Because next to your science in B, you always have instrumental systematics. And so the raw data that you get is a combination of these two types of signals, which you have to take into account. For example, you can see ramps here. Why it should be flat? It relates to the fact that at the pixel level, you have positive hole, meaning that when the photon is coming in, hitting your detector, you create electrons. Some of them will be read out, others will be used to fill these positive holes. And you have an asymptotic response, where behavior of the response of your detector to the incoming flux, which is going to stabilize asymptotic behavior. Then next to that, for example, you have intrapixel variability. If you have photons that falls on different pixels or within different pixels, the response of the substrate will be different. So if you have that combined with some jitter, the fact that the telescope moves, it's a huge bus basically in space, so being stable is tricky, possible, but not necessarily to an infinite precision. Then you have another type of signal that comes on top of this. And you have to take care of all of that in your science model to correct for it and then extract the data. Oh, that's this moment. Awesome. So how do we do this final step in a standardized manner? So what I use is an MCMC. I'm going to draw a bit of stuff in the meantime. So, and what we want to do is build a nice and beautiful model that accounts for instrumental systematics as well as for your science data. So you have to model both within it to simulate a synthetic data. In any of your model, you have a box that will, let's use chi-square, assuming that you have nice white noise, that will compare the quality of the fit, and then it allows you to judge for a given set of values attributed to your parameters set, how well the data that you would have at that point fit the actual measurements through an evaluation of the chi-square, the quality of the fit. Now, the idea of the MCMC is to use a Bayesian approach, to use a random walk in your parameter space to just test and see how things goes. So typically what you do, you start at a given point in your parameter space with a given transition kernel, which means that you have a likelihood of jumping in one dimension or the other. You're testing the quality of the fit there. If the fit is better, you jump. If the fit isn't, then you have a probability of jumping. If you haven't jumped, you do the same thing from the first place. And there is a first phase that is called the burn phase, during which you're going to try to find the minimum while refining your transition kernel. So the way you're about to jump at the next jump. So during the first place, you're going to gravitate, wander around your parameter space, find the local minimum, reshape your transition kernel, and then you're going to populate this place, allowing you to create the posterior probability distribution. Difference with methods such as steeper slope and this kind of thing, that is, it is more robust to local minimum, but it also allows you to go beyond just finding your best estimate. It provides you with an idea of the uncertainty interval as well as the correlation between different parameters. Yes? So
the model, the M in that box.
Yep.
Right. You can't talk about MCMC without having the Bayesian model there specified. So what kind of model are you actually running MCMC on?
Yeah, exactly. So that's why. That's why we here with Nico is because so I developed these MCMC stuff and then I plug in any different kind of model. That's why. So I do some mapping. You can do analysis of surface gravity disturbance or analysis of calcium signaling. So this is why it's a plug and play. Once you develop an MCMC, around which I put some like secret sauce. So the MCMC is actually combining with BFGS, which is broadened. I had my like cheat note because it's a crazy name. Yes, thank you. Yeah, you can use anything to help it like converge. You bring some seeds in it and then you let it evolve. So the idea really is that it's one of the standardized procedure. So so the MCMC really is doing this. So you have your output here that you use in the context of the MCMC. MCMC. So here in the MCMC, you have your combination of x0, chi-square 0, which is the previous state you were at here. You have x1, chi-square 1, which is your trial state. And then the MCMC, the only thing it's doing is, okay, is this a better fit? Yes, no. If it's a better fit or not too bad, then x0 becomes x1, and I'm going to try a new jump, and I restart. If it isn't, then I stay with x0 and I keep on going. And in the meantime, the kernel that allows you to move from an x0 where you are to a tentative state x1 is reshaping. Now, because you start a different place randomly, you have different seeds, and then there are ways to test your seed, but there are also ways to help your transition kernel to be shaped adequately. So the idea, for example, you can use BFGS to assess the Hessian not too far, and then you can use some reshaped version of your Hessian to be your initial transition kernel, for example. Yep.
This sounds very much like a simulated annealing, but only with one point rather than a whole family of estimates.
Yeah.
Is it significantly different in some way?
No, I don't think so. But you can also run, you can run multiple chains and then merge them and then switch from one to the other. You can allow the parameter space the dimensionality of the parameter space to change. It's quite flexible. But the idea here really, in the context of this talk, is that it's a standardized, this is one of the standardized techniques that we can use, and then it's a plug and play. You can remove these things, which is data and model, and then put in Nico's data and a model that relates to Nico's data, and you're good to go. So in this context, so I talk about MCMC. The point really is to, you start, you let it play, it find the spot, and then once in there, it starts to populate the parameter space in this sweet spot, creating a chain, hence the Markov chain relating to the fact that you're jumping from previous states, that populates the posterior probability distribution of your different parameters in this multidimensional space, allowing you not only to get an estimate of the parameter, but also of the precision that you have, all the constraint that you can extract from the data onto this parameter. Now, this being said, I'll let Nico talk about how we can play with other types of data sets, starting from the couch.
All right. Can everybody hear me? Yeah. Okay, thank you, Julien. As you mentioned first, I work in Greka's lab, and we found an interesting way to apply this MCMC to our data. So the bigger picture, why diabetes? The center of my work evolved around lipotoxicity, which is sort of the concept that lipid metabolites are toxic to cells and might underlie like metabolic disease in general. But one of the major models that I'm working are pancreatic beta cells, which are the insulin-producing cells in the pancreas, so kind of the source where diabetes comes from. So these lipid metabolites are mainly fatty acids, which are sort of the elemental building blocks of more complex lipids. And they stress the cell and also eventually kill the cells, at least some of them. And I'm a calcium physiologist. Why would I be interested in something like that? Is because the stress is kind of focused on the endoplasmic reticulum, like an intracellular organelle, which is not just important for cellular homeostasis, but also for calcium homeostasis. So the goal of my work is to use like a medium throughput approach, using like a fatty acid library of like 65 relevant fatty acids, to not just assess cytotoxicity, but also the more interesting part for me, assess how it influences calcium homeostasis and maybe how we can combine these two things and learn something from that. So for non-biologists and maybe also for biologists, I'm going to give you a very quick reminder what calcium signaling is all about. How does this work?
I can be the assistant.
Okay. So it's a very simplified model, but this is kind of how we, from a biological perspective, we think about calcium signaling. Mainly as a three-compartment model, where we look at the extracellular part of the cell as the extracellular medium as with a high calcium concentration, while the cytosol has a very low calcium concentration. It has its magnitudes lower, and a big internal calcium store called like the endoplasmic reticulum. To maintain this homeostasis, there are like different mechanisms. There are pumps that are inherently like energy-dependent mechanisms that constantly pump out calcium from the cytosol to maintain this crazy equilibrium. And we have like channels both on the ER and at the plasma membrane that allow for like targeted increases of calcium. But as well, since we can imagine there's like, I think it's 4 magnitude difference between extra and intracellular, there's sort of a calcium leak, so the membranes are not perfectly tight. So this is kind of how we think about it. And what I do is I measure calcium. And how do I measure calcium? Thank you, mainly by simplifying the system a little bit to actually look at what I want to look at, because I'm interested in the amount of calcium that is stored inside the ER and in other parameters of the calcium homeostasis apparatus. So first of all, I remove the calcium from the outside so we can get rid of this error. So there's no calcium coming in anymore. Also, to trigger like a calcium response, I'm using a chemical inhibitor of all the pumps that are sitting on the ER and actually pumping the calcium permanently inside the ER. So what's left is sort of this passive efflux of calcium into the cytosol, and then the active efflux out from the cytosol into the extracellular space. So the cool thing is that they're fluorescent dyes that are only active in the cytosol. So they basically bind calcium and allow me to fluorometrically assess calcium concentrations in the cytosol. Yeah?
Can you remind me about this context? Calcium is downstream of like a lot of RTKs, that kind of thing. What is it supposed to be doing? What's the everything?
Everything. Yeah, so calcium is extremely versatile. The second messenger in the cells, which does everything from muscle contraction, neurotransmitter release to gene transcription. So it's kind of it's a very cool signaling system that allows for very fast, spatially localized signaling, and also for like temporally more complex things like oscillations and mediates a lot of things like.
So the ER's job is to sequester the calcium.
Exactly. So it's the ER is kind of this big homeostatic part inside of the cell that it basically is responsible, together with the pumps on the plasma membrane, to make sure that this space stays clear of calcium, so we can actually initiate little sparks of calcium signaling everywhere. Exactly. So this is kind of my readout for the status of calcium homeostasis. Exactly. So okay, so we have this model, or like this way to think about and this way to measure it now. So the next thing is using this very simple biological model and translating it into a mathematical model, because what we eventually want to do is plug this in to this cool MCMC. And if you look at this and taking out these two things, we end up with a very relatively simple differential equation that we can actually solve analytically. And it's kind of really maps a little bit into what Julien said before, where we kind of have this knowledge, what I'm explaining here, we have from like a lot of single cell assessments that has been done over the last decades, basically. So we have a relatively good understanding what we're doing here. And what we're trying now is, since I do all the calcium imaging that I do here with an instrument called the Flipper, so it's a 384 well format plate reader that allows me to read out fluorescent intensities in all wells at the same time, so that's a very high temporal resolution. So I'm actually able to do this on a larger scale. And the goal of modeling this whole thing is to actually assess like biologically relevant parameters that are also represented in the mathematical model. So if you look at the next thing, it's a kind of a lot of information on the slide, but let's just start with like the curve that we see here, because this is like the typical ER calcium response curve that I'm observing. So here I'm adding basically this chemical inhibitor of the pumps, which allows the calcium to leak out of the ER, and then all these energy-dependent processes to exclude the calcium from the endoplasmic reticulum. So this is kind of the curve that I'm looking at all the time. So to model this now, we, as the same thing that Julien did before, basically we divide up the signal that we're looking at into two components, into like an instrumental part, the IT, as well as a signal part, which is called the ST. So the IT in our case, we've found that it's relatively well described by just like a linear decay. And the ST is the solution for the second order differential equation, which is a double exponential. And, plugging this into the MCMC, we were quite delighted to see that the fit is pretty remarkable. And at this stage, I also want to say, like, this is basically a 4-parameter fit. And it's not the first time that people try to extract more information from these curves, but I'd say like the more classical approach is to describe these curves more like, okay, where's like the half maximum point? So you just try to describe these curves to compare them, but these measures don't really have a biological meaning, right? You can compare them, but it doesn't mean anything. So the parameters that we extract here actually have biological meaning because they come from the physical model that underlies it. So for example, we have like onset exponential parameters here for the leak, or we have offset exponential parameters for the decay, and K and L is a combination of the extent of the exponentials, which like gives us an idea of the magnitude of the calcium that was stored in the endoplasmic reticulum. Okay, so now considering, or like remembering that this is still like a very, very simple model, it will be like with the power of the MCMC, we actually have the ability to extend this model to, you know, look at further parameters that influence calcium signaling. That's actually what I spent like the first part of my scientific career with, is just modeling calcium signaling on a very small scale. So actually this is a nice way for me to actually connect like the understanding that I developed in the first place, applying it and, you know, using high throughput technologies to look at this in many different states. So, and this will eventually lead, right, I also have some data for you to show like what this actually looks like. So these are measurements from the pancreatic beta cells, and here I'm treating them with different fatty acids, and I just want to show like how like these response curves really are different. Like you have for oleic acid, you see like large increases with like different offsets. Palmitic acid decreases the calcium, while the combination sort of restores it to the control. And we actually use this data as well to model it, to kind of show that, you know, we can actually capture all this variability that we see. We can capture this in the modeling approach that we have, even though it's still so simplified, so much simplified. Yeah, and I mean, putting all this together and maybe considering in the near future like more complex models, we are like hoping to integrate all this data and, you know, with looking at a state, not just with a single readout like the amplitude of the signal, but like a whole set of parameters. We have the power to cluster data, and we have the power to kind of compare different states and get a better idea like what is more similar, what is more different, and maybe that might be more captured in the offset speed than in the peak of the signals. And yeah, this is the eventual goal, is like, you know, creating a lot of data points. Well, this is the principal component analysis, where you kind of reduce all the data points to 2 dimensions for display purpose. But then you want to run cluster algorithms on top of that and, you know, find similarities, and then this will give you, you know, starting points to get more insights into how this process actually works.
Yeah, okay, and
yes.
So this is sort of a total integrated signal for the whole cell.
Yes.
But you had this tantalizing statement that people always make, that calcium can act very locally.
Yeah.
Can you use these methods to do that? Because
No.
I always hear people invoke the locality of the signal, because you might think, whoever is asking, what's calcium's job?
Yeah.
It's to do about 47 different things. How does it possibly do these 47 different things? Because you're overloading one variable. One solution is spatial and temporal. Can you hope to measure any of that using, you know, it's a little bit like these Planetary, how much more can you get out, what resolution?
You really pinpointed there like the limitations, not just of this approach, but also like where all like other modeling approaches are going. So this is measurements in like 384 well plates, so I'm measuring like 10,000 cells at the same time, and I'm averaging over them, so it's impossible for me to make localized assessments. But what I want to do is like looking at the general state of calcium homeostasis and get an idea what's happening. So if you want to look at the locality of calcium signals, you need like much higher resolutions of the microscopes, 2-photon microscopes, maybe even calcium indicators that are more localized to different compartments. And then also the whole modeling of these processes then also gets a lot more complicated, because suddenly we are looking at very small spaces, and suddenly randomness comes into play, and a lot of interesting effects as well.
I'm raising this because it's MIA, and so these might be
absolutely. It's a very valid question.
You might want to have a way to locally, within the cell, by maybe some optical method, cause calcium release there, so you know, disinhibit in a region or something, so that you could really trace it going out. Because otherwise, how are you going to know? I mean, endoplasmic reticulum is all over the place.
Yeah, you can actually do that. There's like
because for the mathematicians, the endoplasmic reticulum is not actually a ball sitting there containing calcium.
I hope I emphasize that this is
but
very
open. So you also have to control spatially release.
Yeah, you can. There's actually techniques to do that. There's like, so IP3 is one of the most, it's like one common second messenger that releases calcium from the endoplasmic reticulum, and they're like caged versions of that. So you can actually shoot with a laser on it, and you can locally So which is interesting, the calcium sparks.
So it's just a data problem.
Yeah.
Chemistry's been solved.
And it's a spatial resolution issue, so like this caged, uncaging of IP3 signals can be done like in oocytes, like xenophus oocytes, which are big. It's harder to do in mammalian cells, but people are working on this kind of thing. There's also, organellar-specific calcium measurements, like Nico mentioned, ER, mitochondrial calcium, which actually, mitochondrial calcium, we have an ongoing project that we're doing now, but not in this sort of higher throughput manner, because you need a much better microscope than our flicker instrument,
Exactly.
which is pretty crude.
Like all this is happening, but we are more in the single cell state on all that. So we are not able to translate that yet.
So the analytical challenge here is, Julien's problem, his planets managed to go around the star in some reproducible way.
Yeah.
All of your cells are different, and yet you want to find out what's the same about.
Right.
And so,
in response to the lipids.
right. So you have to formulate this in some way that you're looking for some invariant property, even though details of the geometry are the same. You have the benefit that you have Newton's laws that are kind of constraining a little.
Hey, you have the benefit of being active player. The only thing I can do is just sit and look at planets. You have a question, you can just go ahead and go for it. This is very good. I am the one that can complain here. You kidding?
You can't just order a new planet.
No, he can, which is what is really cool.
All right, I think on that note, the way we run this is we take a 1 minute break so people can.
Oh wait, it's not done.
So how much more do you have?
There was a conclusion, which is the conclusion that the beauty when we have people doing like a proper standardized work is that we can actually rely on these data points, right? So think about this PC analysis being, cells with their response to like stress factors. You can think about them being planets as a function of mass, radius, atmosphere. You can think about them as being a distribution of habitats, a distribution of life across the galaxy as a function of stellar type, average temperature, composition of the atmosphere. This is where we're going. We're reaching a point where we're building standardized procedures owing to the data quality that we have, the facilities that we have providing this high throughput data set. And so we're really answering a new age of space exploration, and we're proud of being space explorers.